what would be convenient. We have already discussed that on the group. So I think I'll stick to that objective type questions that you can fill out on the Google form. And if there are any figures or diagrams, then I'll put that separately. You can draw it on a piece of paper, A4 paper, and then, take a snapshot and send it to me. Right. But then I guess the time duration is an hour and 30 minutes, right? For the midterms. Right. So let's get started. Any comments or queries, suggestions from your side? Okay. Am I still audible? Just checking once more.
Yes, sir.
Okay. Okay. Right. So if you remember in the very beginning, when we got introduced to the different planetary bodies in the solar system, we were discussing how most of the mass of the solar system lies with the star, with the sun, right? And the remaining less than 1% mass consisting of, largely of gas and dust particles, right? That is what, provides the building material for all the planets in the solar system. And we discussed about the formation mechanism or hypothesis for the formation of the gas and ice giants, right? And we dealt with two models. One was the core accretion model, and the other one was the, perhaps I should ask you this, and then we can get on with the revision. So let us see who can answer that. What were the two models for formation, hypothesis for the gas and ice giants? Ayush? Again, this is completely for revision, so try to participate. We can do a recap in that way. Rishikesh, Manav, जो भी याद आ रहा है बता सकते.
Disk instability and core accretion.
Disk instability and core accretion models, right? And what is the difference between these two models? The core accretion model. Yes, speaker.
Yes, sir. Core accretion, like there is a rocky core over which the gases basically collect, and in disk instability, like within the gas disk that was formed during the planet formation, before the planet formation, there are swirls in there that basically give rise to the planets entirely. There is no core actually.
Yeah, the core doesn't have to form first. In the core accretion model, the center part of the planetary body, basically a heavy core made up of rocky and icy material that accretes first, and then it starts to attract, the gas from the circumstellar disk, and the planetary bodies grow in size. Okay, and the disk instability model, that doesn't require the core to grow first. It's just like, we had discussed about how gravitational collapse of the original molecular cloud that forms the sun. So it's like a mini version of that process, right? So here you don't require rock and ice balls to induce the formation of these planets. They can form directly from the remaining gas and dust in the disk, which collapses under its own gravity, right? So these are the two main hypotheses for the formation of the gas and ice giants, right? And we had also discussed about, when we were discussing about the planet, formation in the inner solar system, we had discussed about what was the timeline of planetary growth, right? And the two main models and the two main growth phases, right? That we start with the nebular disk accretion. If you look at this cartoon over here, initial coagulation, weak van der Waals forces holding nano-sized, micron-sized particles together to give rise to centimeter, millimeter, and then millimeter, centimeter, and then kilometer-sized bodies, right? And for the time duration that it would have taken for a moon-sized body to grow was about, less than 1 million years, about 10 to the power 5 million years. And there were these two growth stages. One was the runaway growth stage, which was a very rapid growth stage because the number of bodies, smaller bodies, was quite huge. And they were, literally colliding with each other, and they were growing in size in a very rapid way. The second one was the oligarchic growth phase, where the growth had slowed down because the number of bodies had decreased, but their sizes had increased. So the probability of collision had decreased just by virtue of, decrease in the number of bodies that were present. But then this led to the growth of Mars-sized, planetary bodies in about a million years' time. And later on, due to later stage collisions, in about 10 to 100 million years time scale, larger bodies such as, the Earth, they grew in size. So we had also dealt how that, the models for the formation of the rocky planets, it's much more challenging, right? But the first few things that we believe that, that led to these particles sticking together were these weak van der Waals forces, right? They were and later on, once the bodies grew in size, right, by virtue of their gravity, gravitational focusing, and other mechanisms, they took over. Okay. And we had dealt with this cartoon. I have removed quite a lot of the slides so that we could just go through the main topics, right? Here I had shown you the main stages of the accretion and growth of the rocky bodies in the solar system, right? So the first in this cartoon, if you look at the top panel, top figure, it basically shows us the solar nebula that it has contracted and formed a spinning disk, right? Out of which, if you look at the second one, the central bleb, gravitational collapse of this, nebula, that leads to the formation of the star of the solar system, which in this case is the sun, right? And a smaller blebs that you can see surrounding, elsewhere in this cartoon, they would basically start to grow into moon-sized planetesimals. And at the same time, if you remember, we had spoken about X-winds, right? That these huge, powerful jets, currents of gas were being expelled from the sun, which also helped carry quite a lot of, expel the gas towards the outer periphery of the solar system. A thermal gradient was also established, right? Extremely hot near the sun and relatively cold towards the outer periphery of the solar system. So quite a lot of volatiles were driven towards the outer periphery, right? Which contributed towards the growth of the gas and the ice giants. And once the gas was ejected in the inner region of the solar system, planetesimals continued to grow by collision. And by that time, the gas giants, if you look at, the picture C, these larger blebs, the gas giants had already formed. So the formation of the gas giants that preceded the formation of the rocky planets, right? And if you look at the final stage over here, planetesimals are accreted or rejected, right? Leaving few large planets that were roughly traveling in circular orbits, right? And we had also discussed why, there's this demarcation between the inner planets and the outer planets in the form of the asteroid belt, where ideally there should have been a full-fledged planetary body, right? But instead of that, we find these broken fragments of possibly a growing planetesimal, right? So, and one of the reasons that we understand would have been responsible for this was the extremely massive, planet Jupiter, as well as, strong gravitational pull. Jupiter is the second most massive body in the solar system, so it exerts a strong gravitational pull on the other bodies, and that is what probably prevented the formation of a full-fledged rocky planet in the region that is occupied by the asteroid belt. And it is known that Jupiter and Saturn, they had also sent, objects from the asteroid belt. Either they attracted it and they were expelled, or pushed towards the outer periphery of the solar system, or they were pushed inwards when they could have been consumed by the sun, right? And remember that the asteroids, they represent just about 0.01% of the material that we think would have survived this entire process, right? And then we spoke about how do we understand about planetary compositions. So do you remember what are the two main ways in which we can constrain the bulk composition of the planetary bodies? Although we do have, okay, I won't give a hint over here. Just quickly, what are the two ways in which, we can understand about the bulk composition or the chemistry of the planetary bodies? Anyone? Rishika, Priya, Saksham, Shubham, Siddharth, Sushmit, Tanisha, Vineet, Mohak.
By studying the meteors.
Yes, that is one way by studying, study of meteorites, which are broken fragments from the crustal part of, different rocky bodies. But what are the other ways? By which we can estimate or get an idea about the bulk composition, about the composition of the material that would have formed these planetary bodies, is by studying the solar photosphere. If you remember, we had discussed this, that we can determine the bulk chemistry of the solar system, right? First of all, we assume that if we consider it like a closed box model, that most of the mass lies with the sun, more than 99%. The remaining mass that would have contributed towards planet formation, just by virtue of the sun being the most massive object, we believe that the remaining material would be similar to the composition of the sun or the solar photosphere, right? And we can estimate the bulk chemistry of the solar system by examining this composition of the solar photosphere by using the absorption lines of elements within its photosphere, right? And that can be converted into the chemistry, right? That what kind of elements are present and to what extent. But the good thing is that we also have meteorite samples, right, in the form of some of the very primitive meteorites, which are these carbonaceous chondrite meteorites, right? And I'd shown you this plot where if you look on the y-axis, we have the abundance of the different elements in the solar photosphere, right? And they have all been normalized in such a way that the units are consistent, it's a ratio. And on the x-axis, we have the abundance of the different elements in the carbonaceous chondrite meteorites. These are a very specific kind of meteorites, right? Radiogenic dating tells us that these are some of the oldest materials that we have access to from our solar system, much, much older than any of the earth rocks that we have been able to measure, right? And their chemistry matches almost completely with the chemistry of the solar photosphere, right? And that can be seen over here, this line of with the slope of 1 over here, and there's almost like a perfect match. So that also tells us that carbonaceous chondrites, they can be treated as analogs, right, or representative of the building material or the bulk composition of the planetary bodies, right? So basically, they provide a very close approximation to the starting mixture of elements that was present within the primitive solar nebula from which the planets formed actually. Okay. Then we had discussed about, the timeline or the age of different major events in the solar system, how with the help of, again, radiogenic age dating, right, we have been able to get some of these numbers, right? So the age that is the most primitive chondritic meteorites, I told you they contain certain, refractory inclusions of calcium and aluminium, right, that have been very precisely dated using the decay of uranium to lead. And their ages were found to be about 4.567 billion years or 4,567 million years. And this is the time which we now generally regard as time zero for our solar system, not for the universe, but for our solar system, right? And this isotope system basically gives very precise and accurate ages for these ancient objects. And if you look at this plot over here, here you have time after the calcium aluminum inclusion formation in millions of years. And then here we have the absolute ages, right? So it all started with the collapse of the molecular cloud forming the sun and gradually other planetary bodies, oldest CAIs on the basis of uranium lead dating, right? And within few millions of years, small planetary bodies started to form, as I showed you in one of the slides, I think a couple of slides back. And already there were plenty of heat sources. Heat sources kya the, which led to melting in the bodies. We had discussed that in one of the lectures. What were the initial heat sources that were, present within these growing planetary bodies that were causing melting?
Sir, I think radioactive processes was there.
Yes, radiogenic, heat sources, potassium, uranium, thorium, which are still present in many of the planetary interiors at that time. Aluminium 26 was present, that was decaying into magnesium 26, right? And also heat from collisional heating, right? When two bodies were, colliding with each other, conversion of kinetic energy into thermal energy, right? And the bodies grew in size, a lot of heat was being produced, the metal separated out from the rocky portion. So basically your potential energy that also converted into thermal energy, right? So there were plenty of heat sources. So planetary cores were getting formed. We had discussed about chondrules when we dealt with your meteorite lecture. These are basically molten or quenched glassy droplets that had formed early on in the solar system and incorporated in several meteorites, right? So basically that's the timeline of different processes that happened in the solar system, right? So this I think we had discussed. There are several isotopes that are used for this purpose. Aluminum 26, magnesium, manganese 53, and these are the decay products with the help of which we have been able to constrain these different events in the solar system in the for planetary bodies. Now, a question came that how old is the Earth? Although the start of the solar system is sort of well dated, right? But what is the age of the Earth and what was the timeline on which the Earth actually started to grow? Because the Earth was not always as we see it in the present times, thousands of years old, billions of years old, right? So believe that the Earth also started as one of these planetesimals, right? Started to accrete mass, and this is the timeline when about 65% of the Earth had formed and the remaining planet was growing in size, and the moon forming event was an important landmark in the Earth's growth because that sort of led to the final growth phase of the Earth, adding the last 10% of the mass of the Earth to it, right? And that the Earth probably continued to accumulate small amounts of material until as late as 4,450 millions of years, right? So then we had dealt with the architecture of the solar system, that apart from the larger bodies, there are several smaller bodies that are also present, comets, meteorites, asteroids, right? And we had learned about what are comets, basically a body that is much, much smaller than a planet, containing a significant portion of volatiles, right, or ices. And we had also dealt how comets are named, how they are classified into long period comets and short period comets. Those that have their orbital periods in excess of 200 years and those that have their orbital periods less than 200 years, right? And we had also dealt with that what are the source regions for the comets. Let us see who remembers what are the two main source regions from where comets originate. Ayush, Anuj, Rishikesh, any one of you, किसी को याद है? What are the source regions for the comets?
The Oort cloud
Yes,
and the
And
Kuiper.
and the Kuiper's belt, right? So these are the two source regions from where we believe that comets originate, right? And what is the Oort cloud? Mohak,
It is an imaginary cloud whose locus has been derived from the trajectory of the comets.
exactly, right? It's an imaginary cloud, right, or a bubble, right, that whose locus has been derived from the orbits of the comets that we observe, and we believe that is the source region for majority of these comets, right? We cannot directly observe the Oort cloud, but we do understand that it's present over there, and by the random orbits of these comets, the locus has been reconstructed, right? And we believe that almost 10 to the power 12 to 10 to the power 13 comets would be present in the Oort cloud in the present times in a shell which basically lies about 103 to 105 astronomical units from the sun. So although the number looks like huge, but these normally have low densities, very small. So we estimate that the total mass of all the comets in the Oort cloud would just be, somewhere equal to the mass of the Earth, which is actually quite less if we compare it with the mass of the gas and ice giants, right? Or the mass of the solar system. And we also dealt with that what could be the compositions of the comets, right? So basically they are made up of various ices, not just water ice, but ice of other organics such as methane, ethane, and they could also carbon monoxide, hydrogen cyanide. So basically carbon, hydrogen, nitrogen rich species. Right. So we'd also dealt with short period comets, which have orbital periods less than 200 years, right? And they cannot be derived from the Oort cloud because of their much lower orbital inclination. So there's a second source, which is the Kuiper's belt, right? And this lies just beyond the orbit of Neptune. You see in this cartoon over here, right? The Kuiper's belt is just beyond the orbit of Neptune, about 34 to 45 astronomical units from the sun. Okay. And we had also learned that all objects in the Oort cloud Kuiper belt, together with the scattered disk objects, collectively known as the trans-Neptunian objects, we dealt with several of these examples as well, right? And we learn about asteroids, which are rocky bodies. They could be, carbonaceous or metallic as well. Can someone give an example of a metallic asteroid which has been in news and which is still in news for quite a lot of reasons?
Recently, a spacecraft had landed on it, but I don't remember the name.
Okay, anyone else? There's an asteroid that has been named as Psyche. It's a largely metal-rich asteroid, right? And we believe it contains, like a treasure of the platinum group of elements. So a few years back, NASA actually had a plan if they could either, scoop some part of Psyche or even drag this asteroid, right? Which could be a potential source of the platinum group of elements. So it was quite a lot in news. Normally before that we associated that okay, there could be differentiated asteroids with a core and a rocky portion, but this was the first time when a completely metallic body was found to be an asteroid, right? Then we had learned about several examples from the asteroid belt, right? For example, Pallas and Vesta, which are two large asteroids, and they are considered to be examples of surviving planetary embryos. Ajay, what is the difference between planetary embryos and planetesimals? Okay, can you provide any examples of a planetary embryo and a planetesimal?
So, planetesimals are those that form at the beginning of the solar system, and means they collide into each other and form planetary embryos.
Right, and it is linked with the runaway and the oligarchic growth stages. For example, Moon and Mars, right? Moon-sized bodies, there can be, although the distinction is a bit hazy, but still that can be treated as a planetesimal, whereas Mars is considered to be a surviving example of a planetary embryo. It's a full-fledged planet. Don't get confused with that. But we think somehow there was some process that prevented further growth of Mars, right? But Pallas and Vesta are considered to be surviving example of planetary embryos, right? Yeah, I had shown you this example of the largest main belt asteroid series, right, which was also recently reclassified as a dwarf planet, and the detection of carbonates, which was considered to be a huge discovery. And why, the discovery of, carbonates would have been considered to be a huge discovery? I think we had also discussed that. Because carbonates are normally dissolved in water as a solution, right? And when the solution evaporates, carbonates precipitate. So if you're finding carbonate somewhere, it could be indicative of, liquid water or solution existing on that planetary body, right? Then we had dealt with asteroids, how they are named, and what are asteroids. Continuing with that, they can be divided to several groups based on their orbits, right, and their reflectance spectra, which is related to their surface chemistry or mineralogy, right? And we had learned about the location of the asteroid belt, where it lies between the orbits of Mars and Jupiter mainly. There are several exceptions as well, right? A few other locations containing the Trojans and the Greek group of asteroids. So then something important about the Kirkwood gaps, that if you plot the distance from the sun and the asteroid population at a certain distance, we found that there were certain gaps which are known as the Kirkwood gaps, right? So if you see, the distribution is not consistent. So these gaps, they are basically representative of Earth approaching asteroids, right? So then we had moved to meteorites. Now, first of all, the difference between meteoroid, meteors, and meteorites. Let us see who can explain, easy peasy.
Any comet or asteroid, any planetary body moving through the space is called meteoroid. When it enters the Earth's atmosphere, it's called a meteor, and when it reaches the surface, it's called meteorite.
Yes, if it survives the frictional heating during its atmospheric entry and can be recovered, it's called a meteorite, right? And we had also learned about cosmic spherules and micrometeorites, just by virtue of their very small sizes, few hundreds of microns, right? And some of these, when they enter the Earth's atmosphere, because of the frictional heating, they get completely molten and then they quench or solidify very quickly as the temperature decreases. So they form these beautiful cosmic spherules, right? And some quick classification of meteorites, first of all, based on whether they are falls, whether they were recovered, following observed falls, or they were found and established to be extraterrestrial samples, but they couldn't be associated with any observed falls, right? Then I'd shown you this example, but let's move on to, yes, that what are the common places where we find meteorites on the Earth? Basically in the cold and the hot deserts, right? The polar regions and in the hot deserts of Northwest Africa, right? And several other places also. But these two, zones, it has been reported that they are the main source regions for most of the meteorites that are present in our collections. We also found meteorites on the surface of other planetary bodies, such as this one that was found on Mars, right? So it could have very well have been a fragment of the Earth's ancient crust. We don't know, that somehow landed on Mars, but meteorites have also been found on other planetary bodies. And then the main purpose why it's important to investigate or study meteorites. I'd shown you this cartoon, which is representative of the different growth stages of a planetary body, starting from material that was present in the solar nebula to a full-fledged, differentiated or layered planetary body that has got a core and mantle crust kind of a structure. And how meteorites, they serve as analogs for these different hidden reservoirs of a differentiated planet, as well as the starting material that contributed build up these planets. So carbonaceous chondrites, the example that we had considered earlier, right? They serve as analogs for the building material of planetary bodies. A quick question, I have already explained that. What is the reason that carbonaceous chondrites are considered to be representative of the earliest, building blocks of the planetary bodies? What is the reason behind that? That Ci carbonaceous chondrites are regarded as, the compositional reference model for the planetary bodies. First of all, they are some of the most pristine, oldest material that have been sampled, right? Much older than any of the earth rocks that we know, very rich in volatiles, and then their chemistry resembles very closely to the chemistry of the solar photosphere. If you remember that, right? Then we had learned about iron meteorites that can be treated as analogs for planetary metallic cores, right? Stony iron meteorites, basically a mixture of iron nickel metal, rocky material that are thought to be representative of a mixture of core and mantle or core and crust material. And then there are these rocky meteorites, stony meteorites that could have been derived from the mantle or from the crust of their parent bodies. We had also learned about the distinction between differentiated and undifferentiated meteorites. Primitive material, basically representative of this first stage, right? And differentiated meteorites that are representative of any of these reservoirs of a planetary body. Once it had got molten and the metal had separated from the rocky portion, right? We call that the body has differentiated. And any fragment from any of these reservoirs after differentiation, right? So they are believed to come from differentiated parent bodies that consist of cores, mantle, and crust. So some of these classifications we had learned about, relation between comets, asteroids, and meteorites, that the main differences, they include their composition, ice versus metal and raw, orbital characteristics, random inclinations versus low inclinations, region of origin, Oort cloud, Kuiper belt versus the asteroid belt, and most importantly, whether they show cometary activity when approaching the sun, basically release of volatiles and dust. Right. So these are some of the questions that we had dealt with, but let's not stick on that. We need to do a quick recap, other things as well. Right, there's geoscattered disk objects, trans-Neptunian objects. We have dealt with those. Some examples of these scattered disk objects, example Eris, I had shown you, made up of right. Let's move on to some of the topics. Right, I'd shown you this example of the Tagish Lake meteorite, this case study we had considered, where many scientists, they believe that these meteorites could actually have a cometary origin, right, or very close resemblance to a comet. Right. Yes, let's go back to this. So this is the roughly, this is the timeline in which different planetary processes took place, right? If we start from times 0 to the present times, right? So we see that after the sun had formed, and very quickly after that, rocky grains, few millimeters, centimeters, they started to form. They continued their accretion fragmentation stage, leading to formation of asteroid-sized bodies, right? Finally leading to terrestrial planets. This is what was happening in the inner solar system. And simultaneously, right, before the terrestrial planets formed, quite an early stage, just after the formation of the sun, right? Again, if we go with the core accretion model, then the cores had formed and they accreted the gas around them. So the gas and ice giants, they had formed in the outer region of the solar system, right? So I think I have shared this slide with you already. Different heat sources that led to planetary melting, radiogenic heat, and together with conversion of gravitational potential energy into kinetic energy, which converts into thermal energy because of impact and accretion processes, right? Core mantle differentiation with the sinking of the heavy iron-rich core towards the center. Again, the gravitational potential energy would convert into thermal energy. Then we have some primordial heat that is still stored in these planetary bodies. So these were the different heat sources. Primary heat sources came from radioactive decay of these different isotopes, right? We spoke of planetary differentiation, how from undifferentiated chondritic meteorites, what happens, what are the different processes, how the material evolves in a thermochemical way, right? Its chemistry changes, basically differentiation happens, and because of high temperatures, and B, that which leads us to a differentiated planetary body consisting of a distinct core mantle crust kind of a structure, right? And in case of the larger planets, we also have a extremely huge gaseous envelope, right, leading to the bulk volume of these planetary bodies. The Earth also, or some smaller planets, they have got a very rare atmosphere, right? Some rarer than the Earth, and in case of the gas giants, that's massive, right? But we learned about, some of, we were going to discuss about planetary interiors and planetary surfaces. We started with planetary surfaces because that is what we have got main access to in the form of remote sensing, mission, satellite sensing, as well as meteorite fragments that belong to the crustal parts. So we dealt with what are the kind of processes that have modified and affected the surface of planetary bodies, different ways in which surface samples, dry surface rocks and samples in the form of lunar Apollo samples that were returned, direct access to Earth rocks, right, meteorites from different planetary bodies, and through remote sensing measurements, we have been able to measure the chemistry of the planetary surfaces. In case of planetary interiors, I told you that it's very difficult, mainly because of inaccessibility, right? Even in case of the Earth, consider a radius of about 6,500 kilometers. All that we have been able to dig into is about 12 kilometers in the Kola Peninsula by the erstwhile USSR, and that is where equivalent to just like scratching the surface, right? But we do have samples from the upper mantle of the Earth, right? Meteorite samples that can be treated as analogs for planetary interiors, right? And then we have, the seismic wave profiles, which tell us about planetary interiors, but that we'll be dealing with our planetary interior module. We got started with planetary surfaces, right? I'd shown you this picture where we had contrasted these different bodies in the inner solar system, Mercury, Venus, Earth, the Earth's moon, Mars, how, the surfaces of most of these planetary bodies have been, affected by these heavy duty impacts, right, forming craters on planetary surfaces. Then there was volcanism that has been detected on the surface of Venus, right? And on Earth, volcanism is still continuing. And we believe that the Earth's moon, if you look at these dark patches on the Earth's moon, right, they all formed because of solidification of lava erupted during volcanism. On the surface of Mars, we have several features, including impact craters and features that resemble like dry riverbeds. And we're going to deal with these processes, basically impact cratering, volcanism, then tectonics and erosion. And out of these, so far we have covered impact cratering and volcanism, right? And different factors that basically, are responsible for these processes, basically planetary size, like smaller planetary bodies would cool off faster, solidify earlier, whereas larger planets, right, such as the Earth or Venus, they would still retain quite a lot of their internal heat, leading to these convective cycles that set up in planetary interiors, which are responsible for, release of heat in the form of magmatic activities or volcanism. And also larger bodies would have more erosion because their gravity that would retain an atmosphere of gas and water, right? Then distance from the sun, too far away from the sun, basically if there's liquid water present, that would actually solidify in the form of ice. If it is too close to the sun, planetary body is going to lose out on the volatiles, right? So just an optimum distance that would allow the presence of liquid water as well as ice as well as vapor, right? But then the presence of these three would lead to a lot of these erosional processes. So distance from the sun is also an important factor to consider how a planetary surface would be modified. Role of rotation, slow rotation versus rapid rotation. So basically planets with slow rotation would have less weather phenomena, less erosion, right? Possibly a weaker magnetic field compared to a fast rotating planet. And then I had shown you this flow chart for the different planetary and geological processes, where you have mass and radius, basically planetary size, distance from the sun, chemistry of a planetary body, and the rotation rate, and how they are linked to the phenomena related to atmosphere, surface temperature, internal temperature, right, even surface gravity, which gives rise to quite a lot of these different processes, such as the greenhouse effect, weathering, erosion, right, preservation of internal heat, right. So coming to impact craters, we have considered several examples of impact craters. We also dealt with that even a small body impacting a planet such as the Earth can be highly devastating, producing energy that is equivalent to the explosion of TNT or dynamite, right, or basically an explosion of an atom bomb. So shown you some examples of impact craters on the Earth. One of the very important one is the Arizona State crater, or the Barringer meteor crater in Arizona, right? And this is one of the very few craters for which fragments of the impactor have also been discovered and investigated, right? I've shown you examples of craters on the surface of Moon, surface of Mars, right? On the surface of Venus, surface of Mercury, and then we had dealt with formation and modification stages of an impact crater, contact and compression, excavation stage, and post formation modification stage, right. So I have also, I think, shared material related to this with you guys. So coming to some of the after effects of how craters are modified, because in case of the Earth we still have most of the craters, they are hidden from our direct view because of the different actions of wind, water, weather phenomena, tectonism, right, volcanism. So they have been hidden, and the Earth's surface has been modified to a much larger degree compared to any of the other planetary bodies. But then there are after effects of crater formation that have been observed on the Earth, and these can be compared. These observations can be compared to our remote sensing observations from the surface of other planetary bodies. That if we see a similar structure, that could be indicative of a impact crater, right? So to see, when craters are modified, basically on the Earth, they can get filled up with water, and water evaporates. That is going to leave out these evaporite mineral deposits. And if such evaporite mineral deposits are found or discovered on the surface of other planetary bodies, that could be indicative of the presence of water, right? Or if there are other anomalies discovered together with that, they could be indicative of an impact crater that got filled up with water and then left out these evaporites over there, right? And in case of the Moon, these are some close-up images. All these dark patches were impact craters that got filled up with volcanic lava, right? We dealt with classification of craters into bowl-shaped craters, central uplift craters, peak ring basins, and multi-ring basins, and shown you what are the main differences between these. At bowl-shaped craters, central uplift craters, by virtue of their size, and some of the other observations that we have in the form of the central peak or uplifted central portion, right? And we dealt with some examples of crater on the Earth, Lunar Lake crater, right? And then very importantly, how we can identify impact craters, right? On the Earth, since most of it, the evidence has been erased, right? So they are localized geophysical anomalies, both gravity anomaly, magnetic anomaly, presence of shatter cones, breccia dikes, molten glass phases, silicate glasses, SUVite, melt rocks, impactites, and most importantly, the presence of high pressure, high temperature polymorphs of the mineral quartz, right? Something that would only have been stable in the deep interiors of planetary bodies, but if we are still finding it on the surface, that means it is in metastable equilibrium and possibly formed because of a collisional event that had produced those kind of pressures and temperatures for a few seconds, converting the normal polymorph of alpha quartz into coesite and stishovite, right? And then we had spoken about iridium anomaly, how most of the Earth's iridium that resides in the Earth's core, but different planetary bodies, meteors, meteorites, meteors, they are still enriched in iridium. So if we find high concentration of the element iridium, that is also indicative of a impact event or basically mixture of extraterrestrial material. Right. So these are some examples that I had shown you of, craters being detected under these huge, ice sheets in Greenland. Yes. This plot I had shown you what was the, past impact rate, the ratio of past impact rate versus, present rate. At almost it was 1 million times compared to the present times. So basically the early planetary history was quite violent in terms of the impacts that were happening, right? And what were the main, timelines for these impacts to happen? That up to about this period, right, between 3.8, 3 billion years back, right, gradually there was a decline and finally there was an exponential decrease. But the timeline is also huge over there. Here we are talking about 4.5 billion years back and the present times, right? So nonetheless, even in the present times, the meteor flux to the Earth is between 10 to the power 7 to 10 to the power 9 kilograms per year, right? And just a simple calculation I had shown you to give you an estimate that how many tons of materials we receive on the Earth in the form of this meteorite flux every day, about 274 tons of material. Although this looks like a huge number, but if you compare it to the mass of the Earth, it's very small, right? And we also, just did a rough calculation that how much energy would actually be produced, right? If a small body comes and collides with the Earth body that has got a diameter of about 100 meters, density of 3.5 grams per centimeter, which is the average density of an Earth rock, right? So we also discussed some of the aftermaths, environmental consequences of an impact event, and very important case study is the extinction of the dinosaurs from the Earth, which we believe they got extinct because of this massive collision that took place in the Chicxulub crater, somewhere between North and South America, in this region over here, right near Mexico. That was this huge impact that created this iridium anomaly, completely hit the covered, created an atmosphere of dust which prevented sunlight from coming in. And the aftermath was that huge environmental devastation, including the extinction of the dinosaurs. And many people, many scientists have linked the timing of this event to the timing of Deccan volcanism in India, which is one of the most massive volcanic provinces in the country, right? Then we dealt with volcanism in the solar system, right? Basically, magmatism or volcanism is the primary way in which rocky bodies they get rid of their internal heat, and heat is mainly derived from two sources: either the original primordial heat left from planetary accretion, or still radiogenic heat that is still being produced in the present times from the decay of uranium, thorium, and potassium, right? And we had also seen this plot where we have time on the x-axis and we have the surface heat flow, how that decreased from 4.5 billion years to the present times. So basically planetary bodies are cooling, how smaller bodies would have cooled off much faster compared to larger planets such as the Earth and Venus. Right. This was just to show you an idea of when these different bodies they cooled up. For example, Earth and Venus, they still have a lot of internal heat. Volcanism is going on. Mars as well, as evident from Martian meteorites. Mercury volcanism possibly stopped, at about 2 billion years back from the present times, right? The Moon volcanism has stopped even few billion years earlier than Mercury. Smaller bodies like Vesta, they cooled off very fast, right? So then some general terms about what is magma, what is lava, right? It's not just molten rocky material, but also carbonate-rich lavas were discovered and sulfur-rich lavas. We also dealt with some examples where, molten sulfur lava was being produced, right? And for example, on Jupiter's moon Io, we spoke about water volcanism, but cryovolcanism, but that is a separate module that I'll cover in the interiors, part of this course. So that we'll deal with separately and in more detail. Then we had dealt with some of the general terms, right? That different subdivisions in a planetary body, just to show you that they are all, differentiated, and where does, molten magma that originates from. Okay. Then we dealt with different compositions, viscosity, polymerization, and volcanism in other bodies of the solar system. I had shown you some of these examples. Again, no need to memorize, but just to show you that we do have constraints on volcanic rocks from other planetary bodies as well, which include lunar mare basalts and the Chagouti meteorites that form, that contain volcanic clasts in them, right? And now we also have some estimates of the Venera basalts on Venus, as well as some of the surface chemistry of Mercury and how that can be contrasted with different volcanic rocks on the Earth, right? And we also dealt with what causes melting in the interior of a planetary bodies that produces the magma, basically increase of temperature, decrease of pressure, or by adding volatile components to the planetary interiors, which decreases the melting point and leads to melting of rocky material, right? We dealt with, mantle plumes, convective cycles, most importantly, these three mechanisms of volcanic eruption, right? It is that the original magma is very much enriched in gases. I've given you the example of opening a can of Coca-Cola, right? So you see there's a lot of gas that is dissolved in it. The moment you give it a vent, gas fizzes out. In the same way, if the magma is very much enriched in gas, right, it's going to go for an explosive eruption. Contrast it with a small amount of gas and contrast it still with a very, very small amount or negligible amount of gas, which is going to be reflected in the eruption style. Gentle lava flow, right, fire fountaining, or a very violent explosive eruption where a pyroclastic cloud is, created. So I think these are the things that we dealt with. Showed you the general structure of a volcano. Skip that. Yes, this connection between the chemical composition of the magma and its viscosity. And why is this important? Because while we cannot directly observe the volcanism that took place many millions and billions of years back, but if we do get an estimate of the chemistry that has a link to the degree of polymerization, which affects how much the lava would actually flow, right? What kind of volcanic landforms it is going to produce, right? And I think yesterday we had dealt with magnitude of volcanic eruptions, how that is measured as a function of mass of the volcanic products, volcanic explosivity index, right, which contains, terms for magnitude, intensity, and destructive power. I've shown you this table over here. The Mercalli scale, which is basically comparing, volcanic activity to known volcanoes on the Earth. And I've shown you several of these examples of volcanism in the Hawaiian Islands that's still going on, fire fountaining on the moon, giving rise to these Apollo 15 glasses, right? And there's still this open offer over here. I'll actually show you later on. I think just after the midterm, we'll get started with our presentations, and I'll make the first presentation. I'll show you some movies as well and some experiments that I conducted in the laboratory on these green glasses, right? Yes, coming back to that. So these green glasses from the Apollo samples, they are a product of fire fountaining on the moon, right? Basically, eruption of lava or magma that contain small amounts of gases dissolved in it, right? And we had also discussed how the size and shape of different volcanic landforms, that depends on several factors, how much material is erupted, composition, physicochemical properties of the magma, viscosity, right? Several of these factors. Then we dealt with flood lavas, right? This is a typical example is the Deccan Plains in India, shield volcanoes, right, in the Hawaiian Islands. Then there were some other examples of shield volcanoes, right? Then I'd also shown you this picture of, shield volcano Olympus Mons on Mars, right? Huge expanse. We had some discussion about it as well, right? And example of this Apus Mons on Venus, which is a radar image of shield volcano on Venus that I had shown you yesterday, right? And this Pateres structure on Mars, how that formed. Stratovolcanoes started with some Earth examples, right? Then these pancake domes on Venus, we dealt with this example yesterday. Right? Link between volcanism and viscosity, right? Low viscosity lava, very thin and extensive lava flows such as the Mare basalt flows on the moon. Shield volcanoes, medium viscosity, lava is still runny, but it is going to produce volcanoes with shallow slopes less than 10 degrees. Whereas composite or stratovolcanoes, those conical volcanoes basically form because of piling up of material at the site of eruption, which makes very steep sided volcanoes which have flanks or slopes more than 30 degrees. And then we had dealt with this case study of combination of impact cratering and volcanism on the moon. Right. So I'll stop over here and let's see. I hope at least some